Good afternoon. I will give you a presentation and an introduction to the use of the software called Vayu Pravah for air movement, which is a free software which was developed with the Ministry of Power and the Bureau of Energy Efficiency with the support of Swiss Agency for Development. So this software has been developed with the support of the University of Applied Science in Sion in Switzerland, and I have been leading the team on this project, as well as we had a good team of people like Gregory Dute, Elisa El Sergani, Loris Layulfi, who have been young engineers, freshly graduated, helping us in the development of the environment. This software can run on Windows 10 PCs essentially, but it has been tested also on Windows 7 or Windows 8.1. We recommend to have something like 16 GB RAM. Maybe it can work with less, but the experience is like this, that we have done mostly with 16 GB RAM. It is part of the Indo-Swiss Building Energy Efficiency Project, which is an Indo-Swiss program joint between the Bureau of Energy Efficiency, Ministry of Power, and the Swiss Agency for Development and Cooperation in Delhi. The particular feature of this software is that it's based on the free OpenFOAM toolbox, which is used by a large community of CFD users, both in academics and large industries, essentially. It provides this toolbox provides meshing tools, fluid flow solver, predefined boundary condition, and post-processing tools. Most of the work can be carried out using specific templates. Two drawbacks of the toolbox, which is freely available from OpenFOAM, is the lack of an easy-to-use graphical interface and its limitation until recently, which was running only on Linux operating system. In between, we have got a new Windows version of OpenFOAM, which has been facilitating the development of the software and its installation in particular. The first point has been the first point was to tackle the development of a user interface in Python language. And then the second part was to link it to OpenFOAM toolbox, which was under a virtual machine initially, but which is now under a virtual machine, but which is directly under Windows 10. So just some of the feature of the software. The computational domain is defined automatically so that the user does not need to play with this parameter. The algorithm have been tested with different strategy. We'll show later some example of that. And this is a typical meshing, an example of meshing resulting from the automatic meshing of the software based on some wind tunnel examples at Hamburg University. Now, if we look at the issue in India, especially, is that there is a very high dense urbanization with very narrow space between the buildings. So one of the questions is, how is the wind direction influencing the air movement between the buildings? Why the building layout, how does it influence the flow between the building, and how also the facade design can influence the cross ventilation potential? One of the first things is that very often design was based on intuition and is still based on intuition than actual calculation. So very often we see arrows, but we don't know if the wind is really following these arrows. And also there are few hand calculation possible, but they are often not sufficient or even impossible when you come to real buildings. So the Fluid Dynamics computational software, CFD, Computational Fluid Dynamics, this is the acronym, can help, but commercial CFD are expensive and out of reach of many consulting companies. And that is why Vayu Pravah, a free software, has been developed so that more people can access the power of the calculation of computational fluid dynamics. And an easy interface has been purposely developed. So now if we look at the possibility of the software starting from a district level, it is possible to simulate airflow in a given direction and a given speed around buildings in a district. Here it's an example of a Swiss town, part of a Swiss town, where a whole district has been assessed for the wind with this software. And the methodology has been developed and validated and published now in the Journal of Physics in the conference series. You have the link here for people who are interested in knowing more, but I will present you now some of the main scientific validation or some example. So here you can see that on a wind tunnel based measurement, so the diamond curve is the measurement on the wind in the wind tunnel. Then you see the fine dotted line, which is done simulated with a software like Flovent, which is a expensive commercial software, but well known and validated. And then you have in the long dashed line, you can see the open foam calculation, which correspond to the engine of Vayu Pravah. So you can see that the results are quite good. Of course, this is just one example. There were many of them already performed. Then another inter-model comparison is the comparison between Vayu Pravah at the bottom and and with Flovent, again with the same case of buildings, just typical square buildings, where we look at the wind going around the buildings, and we see that the answer of the two cases are quite common. They are based on data from the Architectural Institute of Japan. And this is one example, again, of intermodal comparison. Then the other thing which has been developed also more recently is the airflow inside buildings, because initially it was not developed in the first beta version, but it was added later. And already quite a number of comparisons have been performed. And you can see here how in blue, the blue square dots are actually the measurements in an in a wind tunnel model, where the airflow is entering on the left and going out on the right, and you have the different slice where the measurement of the velocity has been taken. And in rows, you can see the calculation with Vayu Pravah of the same velocity profile. So, and you can see that there is a quite good agreement. Now, of course, just few refreshing of the basics. So everybody knows the pitot tube that you see on the aircraft, which is very useful to measure the actual relative velocity of an aircraft with the wind. And you can see that typically you can get a calculation of the velocity depending on the total pressure and the static pressure in the pitot tube. And this is something we can do a similar kind of approach, just to look at how the air, which is reaching a wall at some velocity and which is at zero velocity when it's hitting the wall, comes up as a translation into a pressure. So I don't go in the detail, but you can see here an example. If we see the air flowing, passing far away from a building at a velocity from about 2.6 to 4.7 meters, depending on the height of the airflow. And if now you look at a rectangular shape of 80 meter long and a height of 40 meter, you can see that if you calculate the same way as I showed just before, you can see that if we calculate theoretically with the velocity at about 3 meters per second, what we have in this range here, you can see that the pressure calculated with the Bernoulli equation is of 5.4 Pascal, and you can see that what we get with the software is in the same range. This is not something to demonstrate, is only to show to people that you can get something which you, at some point you can use the Bernoulli equation to get confidence that the software is calculating quite correctly. The same thing is also useful. You can see that we can simulate also the pressure on fins, or the effect on fins or shutters or something. We show here an example where you all the height of the building with some vertical fins, and we can generate then differential pressure to push the air into a building with wind going along the building. Then after, we can see what is happening with the building where we have developed an internal flow. That means I will come back after to explain the method to do that, but you can see that with the wind going along the facade, if we have typical openings, which could be shutters or else, it is changing the velocity along the facade of the building and entering into the building and going out on the other side. In the case, it is a kind of cross ventilation system from facade to facade. And you can see that this is something that can be also looked at with the software. So the main idea of this software is to accompany the design process in real condition, in a sense. First, you have drawings from the architect. So you take them in a DXF format, you clean them a little bit, see if there are too many things, so that you can introduce them into the software, which is quite simple to do. And then you can create a project. Then after that, and create a case and create a variation number 1, and then you can run, after preparing for simulation, the software. Then you get an approximate answer, normally within few minutes, because it's a very fast modeling, purposely with what we call the approximate mode. And then after the running of the simulation, you can do a qualitative assessment of different alternatives, because once you have done one calculation, you can then go back and add a new case and modify the case, or modify the version of the same case. And you see here, just I'll show you later a little bit more about it. So you can generate PDF reports based on the results. And then after, once you have done this block layout analysis, and that you think you can change a little bit the layout of the buildings maybe, then you could go down to detailing the facade and develop internal flows for a typical floor, where you can visualize after the flow into the building at one specific floor, for instance, or more than one, but for if you want relatively quick results, that's how you should. So again, here you just go, you import the DXF plan a little bit simplified, and you can import quite different shapes. It has been tested with many shapes, and so you can even go to a kind of district level simulation with different kind of building, different heights, different shapes, open, closed, etc. Then you can choose how you set the height of the building, if you want to do it separately, building by building, or all together. You can also then, after, prepare the simulation. That means you set up the environment. That means typically the direction of the wind at a reference height, and then you choose the number of CPU that you allocate to the calculation. And then during the simulation, you get the pop-up windows. It's showing here, you see the meshing. That's the meshing. The meshing is the preparation of the model actually to run OpenFOAM. And then after, you can see the time remaining. Once the meshing is completed, you have a bar here showing the typical time remaining. So for many block kind of model, it takes few minutes. Germany, it's generally less than 5 minutes to get an answer. And then at the end, once you get it, you just have to click on this button to get the results. And then you can visualize the airflows in different variable and different parameters. And then you can visualize them for different kind of things. One is the velocity at different levels or different. You can have plans which are horizontal or vertical in both directions. You can have the pressure. You can add arrows which show the velocity also. You can have something very interesting for people who think about creating pressure difference between facades of buildings. You can have the pressure directly on the building facade. That means you show only the buildings and you can just add labels. Then you can look at the streamline. This is more indicative, I would say. Another interesting thing are threshold. That means you can look at, for instance, when the velocity is low, which area are really in this typical volume, or you can also have clipping plane. That means you can cut into the building where you have created one open floor to see how the air is flowing from inside to inside and then from inside to outside. Then after, you can modify your project either by moving the building translation number 7, for instance, or you can also rotate it. You see that the building number 9 has been rotated. So this is just showing you some of the basic. So you can have one base case and then you can have a modified case later on. Then after, from the different variation, you can get PDF files where you can compare at the same height for the same window conditions. For instance, here you see at 12 meters approximately, you see the different velocities with the scale, and you can see how the velocity is impacted between buildings by the kind of building layout that you have. Then after, one feature which is quite powerful also is that you can have what we call layers. That means you can create, let's say, the base block of a building, which goes from bottom to one floor level that you choose. And then you can add some facade profile. Then after, you can another facade profile with opening. And this is what we show here, the A, the B and C typology, which are on top of each other. And then again, the B and C on top, so that you have at one floor, you have the sill, then you have the openable part, and then you have the sill again, and then you have the under the ceiling, sorry. And then after, you can add a block on top to make the complete height. And this allows you to calculate then the airflow going into the building. So this example show you here how the air, when the wind direction is perpendicular to the longer facade, if you have 3 buildings, one behind the other, you can see that the airflow in the first building is quite high. You can see that we reach velocity of almost 1 meter per second inside the building, and that the next one and the next one, the one behind is getting hardly any wind. Now, by changing the layout of the building, of course, this is a schematic case to demonstrate the possibility. But now, if you have windows opening with kind of shutters or window opening in the right direction, and in the right direction also on the back of the building, you can see that we can transform the velocity which is going quite along the facade by internal flows, and it's quite well distributed between the three buildings as compared to the previous case. These are the same building, the same characteristic, but simply arranged differently. So we can see that it's possible to look at the global flow around buildings and then see whether we can transform this velocity or this pressure into actual airflow through the buildings. So as a summary, we can say that Vayu Pravah is a freely downloadable real CFD, which people who register can get. It gives results for most of the typical block cases in few minutes. It allows really optimizing in real time during multidisciplinary working meetings. If you think of architect, client, developer, and then engineers around that can discuss, or green building consultant who can discuss together on the different solution and gets very quickly some design direction and a basis for decision also. So it is a good addition to Econivas Samhita in the sense that Econivas Samhita is a code which is very well developed to reduce heat gains, and which also specifies the minimum condition to be able to get a good natural ventilation. But this tool allows to go beyond that in the sense that we can look at a group of building and look how we can get the wind helping at natural cross ventilation at night especially. So thank you for your attention.